Alright, this one says, in the figure below, the length of the distance between the screen and the barrier here is 1.2 meters. This is a double slit experiment because we have two slits separated by a distance d. This is the barrier, which blocks light from coming through except for these two openings. And then we have a screen on the right side. Distance from the barrier to the screen is 1.2 meters. The separation between the slits is 0.12 millimeters. And we have a wavelength of light of 500 nanometers. Now this one's a little different from ones I had done in the past, because ones I had done in the past were all about what happens at a bright fringe or what happens at a dark fringe. In this case, it's going to be between fringes, potentially. It wants us to calculate the phase difference between the wave fronts, arriving at point P here. And theta is approximately 0.5 degrees, which is a small angle, and that's common for these problems because the screen is so far away from the barrier. And we assume that the paths are approximately parallel. We're doing what's called the small angle approximation. So we treat the rays as parallel. And then treat this angle as 90 degrees. Alright, so the path length difference is important when it comes to finding the phase difference between the waves. So we're going to assume that this can be given by the formula d sine theta. Alright, so let's find out how long is that d sine theta. So let's plug in our distance between slits. And then we'll multiply by the sine of 0.5 degrees. Let's see what we get there. I get that the path length difference is 0.000001047 meters. Alright, now we also know that the wavelength of this light that's being used in the experiment is 500 nanometers. So we got to find out, like, what fraction of a wavelength has been completed. To do that, you could divide the path length difference by the wavelength, and it would give you a certain fraction. So 0.000001047 meters divided by 500 nanometers. Okay, it's giving me a fraction of 2.094. Now, what's the meaning of that? this means that 2.094 extra wave cycles have been completed by the light taking the lower path versus the shorter upper path. Okay, now, if we want the phase difference, then we should turn it into an angle in degrees or radians. Right now, the units of this would be cycles. Okay, so if we want the phase difference here, take your number of cycles and then convert it by multiplying by the fact that there are 360 degrees in every cycle. Okay, so we're talking about 754 degrees. So you could change that phase difference, make it 0.094 cycles, because it doesn't really matter how many full wavelengths have been completed. But what we care about is the fraction of a wavelength that's been completed. So this will give us that. Looks like about 34 degrees. Now if we want that in radians, we could do times 2 pi per cycle. Sometimes radians is easier to work with for certain types of problems. I get 0.593 radians. If you want to keep the phase difference including all the completed waves, then you would do this. Yeah, it comes out to about 13.2 radians. Yeah. Alright, what else do they ask? They say calculate the phase difference between two wave fronts if y is equal to 5 millimeters. There's a relationship between lambda and y. So for that I would use the formula y equals m lambda L over d. Because now we can plug in the vertical height. And when they talk about the vertical height, they're talking about this height here from the central maximum from the center axis here to the point P. That would be y. So we'll do 5 times 10 to the minus 3 meters equals m times 500 nanometers times our distance to the screen, divide by our slit separation, and we want to solve for m. Find out how many cycles have been completed. Okay, so for this, I actually get that m is 1. So 1 cycle has been completed. Now keep in mind that this was the formula for bright fringes. And so since it is the formula for bright fringes, and we got an m of 1, that means that this is the location of a bright fringe. And if that's the case, then the phase difference between the wavefronts would have to be 2 pi radians. Or you could say there's no difference between the waves, because they would be constructively interfering at that point. Next question says, what is the value of theta for which the phase difference is 0.333 radians? We'd like to take the phase difference and divide by 2 pi to figure out what fraction of the wave has been completed. That'll be the number of wave cycles completed. So let's put in 0.333 radians, divide by 2 pi radians. We get 0.053, and that's the fraction of a cycle that's been completed. So now we can look at our different formulas that we have for double slit. One of the formulas we have is theta m equals m lambda over d. This is also for bright fringes. So let's let our wave number here be this fraction. Let it be that 0.053 of a wave has been completed. Multiply by our wavelength, divide by slit separation. So the angle, which is this angle here, is going to be 0.00022 radians. If we convert that to degrees, it's 0.0127 degrees. Last question. What is the value of theta for which the path difference is 1/4 of a wavelength? Let's set lambda over 4 equal to d sine theta then. So we'll get this. Let's also plug in our wavelength. Our wavelength was 500 nanometers. So we can solve for theta. 0.0597 degrees, which would be 0.00104 radians.